In lesson 2, we're going to talk about how to solve a linear system using substitution. So this is going to be one of the methods that we're going to talk about, how to solve systems algebraically, and then in the next video we'll talk about a second method. So for substitution, what you're going to do is you're going to solve one equation for x or y, and then you're going to substitute that expression into the second equation. And then you'll solve that equation for either x or y because it'll be all in one variable. And then once you figure out x or y, you plug that back into either one of the original equations and you'll get the second variable that you need. So let's look at some examples so this will make a little more sense to you. So this first equation here, I want to solve it, or this first system I want to solve by substitution. So what you want to do is you want to look at your two equations that they give you, and you want to see if one of the variables is already by itself. So if you look at this second equation, see how y is already by itself. So I don't have to solve anything first. So what that means is I can rewrite this first equation, and instead of writing y, well, I know y equals 2x minus 1. So I can take 2x minus 1 and plug it in. So I'm going to rewrite that first equation, and wherever I have a y, I'm just going to put parentheses, and then I'm going to replace my y with what y equals, so 2x minus 1. And then the parentheses in this case are just going to drop because it's just a 1 in front, so I just distribute a 1. And now you're going to solve so that you can solve for x. Once you've eliminated the y variable, now you can just solve this equation for x and figure out what x is. So I'm going to just group my like terms. So I get 3x minus 1, add 1 to both sides. So I have 3x equals 3. And divide both sides by 3. We get x equals 1. So x equals 1 is my solution for the x, but I need to make sure I get solutions for x and y because this is a system of two variable linear equations. So now I'm going to take this and I'm going to plug it into either equation. So you can plug this into either equation. Plug into either equation. It doesn't matter because it has to work in both. So I usually try to pick the easier equation. So if I look ahead, the easier equation is going to be the second one because it's already solved for y. So I'm going to plug this into y equals 2x minus 1. So y equals 2. I'm plugging in 1 for x, which is what we found. So y equals 2 minus 1. So y equals 1 as well. So now, just like when we did this for graphing, we want to write our solution as an ordered pair. If you think about this on a graph, these are two lines, the original equations in the system, where when they cross, they would cross at the point 1, comma 1. So that's your solution. And now you can check that if you want. You can plug it in, and you'll see that when you plug it into both equations, it ends up working. So let's try another example. So for this one, we want to solve by substitution. So now the difference in this example compared to example 1 is the fact that when you look at both of these equations, neither of them are solved for a single variable. But if I look at this first equation, it's going to be pretty easy for me to get x by itself since there's no number in front of x. So what I'm going to do is I'm going to take this first equation and I'm going to rewrite it so that x is by itself. So what's going to happen is this is going to be x equals 3y minus 1. I got that by adding 3y to both sides. That's what I did. So then the second equation I'm just going to leave as is. Let me just rewrite it over here. So it's 2x minus 3y equals 4. So now what I'm going to do is I'm going to take this first equation, and instead of having x in the second equation, well, I know that x is equal to 3y minus 1 based on the first equation. So I'm going to rewrite, and again, we're using parentheses wherever that x is, minus 3y equals 4. So I just copied the second equation, and now I'm going to plug in 3y minus 1. So 3y minus 1. And now since I have a number in front of the parentheses, my first step is going to be to distribute that 2. So I get 6y minus 2 minus 3y equals 4. And you're just solving this equation for y. So group your like terms. So I have 3y when I subtract 6y minus 3y minus 2 equals 4. Add 2 to both sides. So I have 3y equals 6. Divide everything by 3. We get y equals 2. So now I take that, remember, and you can plug it into either equation. You still have to find x. So you can plug into either equation. So take this, and let's look at which equation is going to be more convenient. Now, it's probably going to be more convenient to plug it into the first equation because x is already by itself. We're not going to have to worry about that 2x. So I have x minus 3y equals negative 1. And I'm going to plug in what I got for y, which was 2. So I have x minus 3 times 2 equals negative 1. So we get x minus 6 equals negative 1. Add 6 to both sides. And we get x equals 5. So again, your solution is not to say x equals 5 and y equals 2, but it's to write it as an ordered pair. So 5, comma 2. Make sure that you put the x value first. Even though we found the x value second, this is an ordered pair in x, comma y. So it's got to be x first, then y. All right, let's look at a couple more. So this system here, first look at both equations, see if one variable is already by itself. So in this case, the second equation already has y by itself, which means I'm going to take the second equation and replace y in the first equation. So I'm going to replace, first of all, I'm just going to put parentheses wherever y is. And then it's, okay, well, instead of having y in that first equation, we know that y is equal to negative 2x plus 4. So you replace your parentheses or your y value with what y equals. And now you have x all by itself, or an equation with just x. So now we're going to just solve this equation for x. So I have negative 4x plus 8 equals 8. So then from here, I notice that when I combine my like terms, these cancel. So I have 8 equaling 8. So this is one of those unusual cases where your x values cancel and you're left with something that's always true. 8 always equals 8. So this is always true, which means it doesn't matter what my x and y values are. This statement is always going to be true. These equations are actually going to end up being the same equation. There's infinitely many solutions because it doesn't matter what x and y is. 8 is always going to equal 8. So if you ever get a case like this where the x's cancel out and you are left with a true statement, this is a situation where you're going to have infinite solutions. So you don't have to go any further with this because you've got a true statement that's always going to be the case. It doesn't depend on x or y. If you look at the equations, if you imagine solving that first equation for y, so you would bring the 4x over, divide everything by 2, you would end up with y equals negative 2x plus 4, which means you got the same equation, so there's infinite solutions. So then the last scenario here is one last example, and let's take a look. So if I take this second equation, which is already solved for x, and I plug it in, again, use parentheses first, so plus 6y equals 7. In this case, I'm replacing x because x is what I'm told is equal to negative 3y plus 5. So go ahead and distribute. So negative 6y plus 10 plus 6y equals 7. And we go ahead and we notice when we combine like terms, these 6y's are going to cancel, But this time I'm left with 10 equaling 7, which is never true. So this is never true. So that means if we get something that can never work, that means there's no solutions. These lines would never cross because you're getting something that can never happen, which means the lines will never cross to create a solution. Again, compare the original equations. If you got this first equation so that you solved it for y, and the second equation so that you solved it for y, you would notice that the lines have the same slope but different y-intercepts. So the graph would be parallel, where in this previous example, these two equations would have same slope and same y-intercept, which means they're the same. So those are your unusual cases when we're looking at solving systems algebraically. If it comes out where it's always true, it's going to be infinite solutions. If it comes out where you get a situation that's never true, it's going to be no solutions. Otherwise, you'll always just get one solution.